everyone here and everyone online. I'm actually Saeed Ahmad Salehi, and my student, no problem. My student had some problem and she couldn't join, so I'm going to present. It will be a short presentation about efficient stochastic computing-based circuits for servomotor controllers. So first I will introduce stochastic computing, what that is, and then I will talk about a general picture of servomotor, and then the proposed work, and finally, and then I will have some simulation results, and finally the conclusion for this talk. So stochastic computing, what is stochastic computing? Traditionally, humans use positional encoding. It means that from right to left, we give weight to every digit that we have. And for example, this is a decimal number, and we have ones at the right, and tens, and hundreds, and so forth. And the value of the signal will be, the value of this number is just the weight of each digit multiplied by the value of the digit and the sum of everything here. And for computers, we have the same positional encoding, but for the digits could be only zeros and ones. For example, you see this number here, the value is calculated by multiplying ones and zeros to the weights, and the final value will be achieved. But although operating on positional encoding numbers is very compressed, and it's very efficient to represent numbers, but operation on those numbers is hard to implement and complex. That is why people are working on a stochastic unary encoding, and this representation doesn't have any weight for digits. In this representation, we use a bit stream and actually a random bit stream to represent a number. For example, value of X is represented by a bit stream of zeros and ones, and the value of each bit can be randomly 0 or 1 based on the probability that we have for that number. For example, if we want to represent value 7 divided by 16, then we have 16 bits, and out of those 16 bits, 7 of them are ones which are randomly positioned or placed in this bit stream. Of course, if you have more bits, you can have more precision for your representation. This representation can provide some benefits for us. Before that, I want to refresh your mind about probability law that we have. Let's say we have two boxes, and each box contains black or white balls here. And assume you just close your eyes, take one ball randomly, from one of these boxes, and then with your other hand, you take another ball from the other box here. What is the probability of these two balls that you took to be both of them to be 1? I guess you remember from the high school that the probability actually is the probability of having one black ball from the left box multiplied by the probability of having a black ball from the right ball. That gives us an inspiration to use an AND gate for multiplication. What I mean by that, let's say we have this AND, and the top input X can have a random bit stream with the length of 8. Of these 8s, 4 of them are ones, the other 4 are zeros. The bottom input, 6 of these 8 bits could be 1, and the other 2 are 0. The probability of having the probability in the output of having 1 will be 3 over 8. It means that with the chance of 3 over 8, each bit of this random bit stream is 1. And 3 over 8 is actually the multiplication of the probability of having 1 in the top input multiplied by the probability of having 1 in the bottom input. So it means that by a simple AND gate, we can implement multiplication, assuming we have a random bit stream for each of the inputs that we have. So compare this with a traditional or conventional binary multiplier that we had. For example, here I have a 32 or 16-bit multiplier, and each of these small boxes here are either half adder or full adder. I guess you remember from digital design that half adder is composed of 2 gates, an XOR, and also an AND gate, and full adder at the bottom here is composed of 1, 2, 3, 4, 5 gates here. So when you see how many gates we need to implement a 32-bit AND multiplier and compare it by a single AND gate, you can see how good it is to have stochastic computing. But of course, there are some challenges here. But before that, actually, I have to mention another benefit of stochastic computing, other than having less area, is that if you compare the critical path of the traditional multiplier with an AND gate, which is a simple AND gate, you see that how fast would be a simple stochastic computing multiplier. But there are some downsides for sure for this. One is that how we actually generate that random bit stream efficiently to implement this. The other one is that if we have only one single AND gate, you need a long bit stream in order to achieve high accuracy. And it means that the number of clock cycles that you need will be increased by the accuracy or precision that you want. And these are something that people are working on that. But for this project, we try to just use the advantages of stochastic computing for implementing a servo controller. Yeah, I guess here I mentioned here, I showed here by another example how AND gate can implement multiplication. Also, another important operation that we can use by stochastic computing is addition. Here you see a simple multiplexer, 2-input multiplexer, that can perform scaled addition. Scaled addition means that the output of the multiplexer is a scaled addition of 2 inputs that we have. For example, for these cases here, one of the inputs is 3/8, means that the 3 of these 8 bits are 1, the other input is 7/8, and this select signal is 1/2. And the output is actually the scaled multiplication of these 2 inputs, 1/2 of the addition of X and Y. And this is something that you can prove always is true. So we can implement multiplication by AND gate and addition by multiplexer. Now, how we can use it for a servo motor? So this is a big picture of a servo motor controller that you see here. We have PID controller here. We have PWM generator, and this is the motor that we have, the rotor. And this is the measuring circuit that measures the rotation of the motor and produce a feedback signal. This feedback signal is subtracted from the desired position or the command signal where we want the motor to stay. And then this, the error or differences between feedback and command will provide the error, and the PID can generate the PWM, change it such that the motor goes to the place that we want, to the angle that we are expecting. So this is the servo motor controller. And now I'm going to briefly explain different parts of that. The first step is here, the encoder. And you see the encoder can be implemented by this detector here that we have 2 diodes here and the receivers. And based on whether the output of this, when the rotor rotates, we have these pulses here because there are some gaps here. If the rotor rotates clockwise, we have this for the A and B. And if it rotates on counterclockwise, then the B will be leading than A. So it means that here, for example, on the rising edge of the A, B is low, but if the direction is the opposite on the rising edge of A, B will be low. And this is the way that we can detect the direction. This is a digital decoder that can provide for us the direction. Either 0 or 1 means that it is clockwise or counterclockwise, and the position of the rotor that we have. So we have these two values, the direction and the position. The PWM generator of the schematic that I showed you for the servo controller can be implemented simply by a counter. So here we have the PWM counter, and it compares to the position counter. If it is more than that position, generates high. If it is less, it generates low. And this way it can control the duty cycle or the width of the PWM signal. The PID controller parts is composed of these three parts: the proportional part, which is simply a multiplication, and the integrate part that takes the integral of this error, and the differential or the derivative part that just takes the derivative of this feedback signal. And these are combined together by this adder to generate the output for the signal that we have. So you see everything here is multiplication and addition and subtraction that we can implement by stochastic circuits. Here I just listed this in this table, what each portion of this PID controller implements. These are mainly the control topics. I don't want to go details for that, but you should just know that some of them are doing, for example, the value is decreased, the output of these values, or increased based on this situation that we have. For example, for the proportional block that we have, in the rising time, it increased, the overshoot time is increased, and the setting time, it has a small change, and a steady state error is decreased when you have a proportional circuit. So these are control topics. I don't want to talk about these. But what the proposed work is, as I mentioned, is that we are trying to map we actually mapped different blocks of the servo controller to a stochastic computer. The first step the first block that I explained is the integrator part. So rather than implementing integrator by some complex calculation, we propose to use this equation or implement this equation to implement integrate. So I guess you can see that this equation, the output yn, is actually the integration of the xn. If we take the previous value of the output, add it to the current value of the input, and then again, we keep doing that. So this equation is simply implements discrete integration for us, and we can implement it by stochastic computing. These are two circuits that can do that here. One of them, we directly use the MUX, the multiplexer, and this is the delay unit that we have, because in stochastic computing, each number is represented by a bit stream. So it means that for our delay also, we need to have a shift register rather than the simple flip-flop or register 1-bit D flip-flop. Here we have a sequence of or a shift register here. Another circuit that we used actually is more efficient than this one, because if the length of the bit stream is too long, the number of flip-flops in your register will be increased, and that's not a good design. So in this method here, we use an n-bit up-down counter and a comparator. And we have a pseudo-random number generator here. So the input x that we have is connected to the up counter of this counter, means that when this input is 1, the counter goes or counts up, and the complement or the not of this x is connected to the down counter of this one. So whenever the x is 1, the value or the output of this counter is incremented, and whenever it is 0, the value will be decremented here. And it is compared to the this random number generator. If it is more than this value, the output will be 1, otherwise the output will be 0. So obviously you see that when your x is 1, you have more ones. It means that the value of x is higher, and it means that the integration in the output will be higher. And I don't want to go through the details of that, but we can prove that this circuit is actually implementing integration of the input more efficiently compared to the circuit in part A or figures A. We also made some modification to this, and I don't know, can I remove this part here?
Wait some more. Yeah. Cool.
Oops. So by modification, we replace the random number generator that we have with a fixed offset. What is the benefit of that? Two benefits. First is that we just save area because we don't need any random number generator anymore. The other one is that by controlling or changing the offset value, the fixed value, we can actually control the output of this integrator. And this offset can come from the feedback, and this way we can provide a control circuit. This is the flowchart of how to use offset to control our circuits based on the PIDs. Again, I'm not going through the details of that, but what we do, we just compare the feedback signal with the command signal, and based on that, we increment the counter or decrement that. This shows different possibilities that we have. For the detection of the direction, we use the XOR here. For example, if the feedback comes first and then the commands, then we have this that shows the direction, whether they are in the same direction or they are in a in a different direction. And also we use AND and OR gates also to generate the PWM that we have. If the error and integral output, for example, we OR them together in this way, the output of this will be the longest value of integral and the error. So whichever is longer here. And we use AND gate to make the kind of like the minimum of these two inputs, error and max. And when we have the minimum and maximum, we can control the value here. So based on the direction and the difference between error and integral signal, we can control the output of our PWM. This is the circuit for decoding position and control that can provide for us the direction and also the position that we have. And based on that, we can have a faster servo controller. By faster means that we have direction, whether they are in the same direction, I mean the feedback signal and the command, or they are in the opposite direction. And also we have the difference between them, a position here. And if they are in the same direction, then we increment the counter that we have in our system slowly. I mean, for example, +1, and it should be -1. But if they are in different direction, it means that the motor should rotate faster. So rather than incrementing or decrementing by 1, we increment or decrement by 4 here. It should be -4. So we speed up the control circuit here. These are the results that we have for different implementation. The red one shows the binary or traditional binary computing one, if we just use traditional logic circuits. And the green one here, the blue one shows the first method that I showed you, and we just simply use the multiplexer for addition. And the green one is after we applied some modification or optimization. For example, we replaced the multiplexer circuit by the counter circuit. We also use the AND gate or gates to calculate the minimum and maximum of these two feedback signal, integral signal and error signal. And after that optimization, you can see that the area is reduced. And both of these stochastic computing base are less area consuming than the traditional binary computation base. The power, dynamic power is also reduced here. And the speed for our system that we can control the system has been increased significantly based on this stochastic computing circuit that we have. So the conclusion is that if we can use stochastic computing for this servo controller, because the servo controller is composed of addition, subtraction, and multiplication, and those operations can be efficiently implemented in stochastic computing, then we can achieve higher speed, lower power, and less area consumption. The future direction is that actually we have already implemented this on FPGA, we got the results, but we want to connect this to actual servo controller and future. This is the direction of our research for this topic. Thank you, and if there is any question.